Ave all, I am Zoltán from Hungary, HVACtuner.hu. So here is my first English video. Let's see what we have. So here you can see a building without roof. Actually the walls and half of the building is isolated with 30 centimeter thick EPS isolation. The other side is not isolated, as you can see, and the wall is 30 centimeter thick, and the typical Hungarian brick is the material, the B30. It's a burnt clay brick. There are walls inside, so it's not the small size brick. And let's see a section view. Yeah, we have to wait for the computer because I took back the capacity. That's why the fans are in silence mode, but we have to wait more time to see the views. Here you can see only one layer in the floor. It is 10 centimeter concrete here as well. This is the same material as here, so it's just soil, and the outside is the same soil. But we are going to the other side of the building. Zoom outside, come down there. Here you can see that's 10 centimeter EPS isolation inside. And I added, if I could remember well, the same heat load in every room. And if I can remember well, it's 20 watts per cubic meter. That's why I took this. If the heat load is the same in every room, find out what will be the temperature inside. That's why, because lot of ordinary person, I mean not interested in HVAC or building physics, thinks that it's easy to calculate the heat demand because it's only the cubic meter or the square meter is the interesting thing, and they can multiply it with the magic number. But of course, who knows the building physics a bit better, that know that it's not so simple because we don't have the magic numbers. No, see what we have here. So as you can see, if the room it's not isolated, sorry, so put that annotation here. So it says here it's 20 degrees. That is 25 degrees, as you can see. So the isolation on the outside helps us to increase the inside temperature, of course. But what about the floor? Is it the same or is there any difference? We are looking from the top, and as you can see here, we have the floor isolation. You can see there. This the 20 centigrade area is much larger here. See in section, maybe better, maybe. And change the section axis. 0, 0. Sorry. Yeah, it's very slow, but if I turn on the performance, you cannot hear me because of the fan wheel. We're always on the maximal RPM. So the same floor here, but the isolation outside. Of course, the soil under the isolated room will be higher temperature. Sorry, I cannot use this query icon here because I don't know why, but it cannot work on section view. So that's why I will use the scale here to match the colors to that scale. So it says it's around 7 or 8 degrees in the middle of the room. Here it's around 5, 4. What about the outside corner? As you can see, it's quite cold. It says it's around 1 degrees. But here it should be warmer. And yeah, of course, it's 5, 7. Yeah, here we don't have any isolation here, that's why. If we are going to the other side of the building, here you can see the concrete itself. I mean, the concrete floor will be higher temperature. And below the isolation, of course, it will be colder. But the room itself will be in higher temperature. And that's why it's very important to make this vapor isolation well. Because vapor always finds the smallest hole to go to the place where it can condensate. So if here is some gap and no vapor isolation, vapor will come here and condensate there, and it can fill up your soil with water. And if there is any food for the molds will be grow there. See the other side. Ah, sorry, I turned it. Turn back and pen. Yeah. So here temperature is around 6 degrees. But compare only the floor. Let's see. I hope that will be the section axis. Maybe not. We'll see. No. And then try with the X. Yeah. And move it on the side. It's too much, maybe. Come a bit closer. Yes. Here you can see the outer isolation is missing on this side of the building, and we can compare now only the floor isolations. Zoom out. What you can see here, of course, where we have the isolation, the soil is colder. It's better for the heat efficiency, but it's also worse in terms of the vapor condensation in the soil. As you can see, the soil is much colder here than there. Let's see your heat flux. It takes a lot of time. Yeah, without isolation, the outside corner takes the most of the heat from the room to outside. And it's the same with the isolated as well, but as you can see, the outside heat it's much higher here. Turn off this section view. Here you can see the flux, heat flux. The isolation on the wall doesn't goes down in the soil at this model, and that's why you can see the heat comes outside. So that's why it's important to put the isolation also in the wall, or go back to section, and maybe it's better to see there. So isolation must go here, or if you cannot put the isolation in the soil, then put there. It will also work because the heat comes this way. I switch back to the temperature. So because the heat is perpendicular to these temperature lines, isotemperature lines. And if you draw the perpendicular line here, you can see the heat flow there. This Prepomix software cannot show you any arrows, unfortunately. So that's why you have to use your mind to find out the heat directions, but it's not impossible if you think a bit. Yeah, the heat conduction, of course, much better in the soil than in the isolation. That's why you can see the cold comes closer to the wall, not like in this isolation there. Okay, go back to outside. Yeah, and as you can see here, the exterior corner, it seems colder. Why? Of course, because there the length of the way that the heat should pass, it's much longer, as you can see. The direction is this one because it's perpendicular at the isothermal lines, so it comes here, but it's much longer, of course. After Pythagoras, we know it. And if we see here, should find to rotate it somehow, but I cannot do it. So as you can see, at the middle of the room, the temperature is higher. Why? Because this one also takes out the heat to the ground, this middle wall. And this corner as well. I will show it in section view. Here you can see the thermals. Okay, and switch to flux. It's interesting actually. I don't know why that flux. It's smaller there. I cannot understand. Should be higher. Because the temperature is also lower. Yeah. The temperature is low here. So the heat have to come there. And it's straightforward that it's lower there. Because the walls takes the heat to the soil. Yeah, probably that's all I wanted to tell. Or maybe check the outside. Mhm. It's also interesting thing where the isolation finishes. You can see the temperature, it's higher there. It's much higher here than the temperature here. Why? Because the wall, which is isolated, it's warmer. And that heat comes out here where you cannot find any isolation. See from the top, yeah, perpendicular to the isothermal lines, the heat comes out there. And if I switch to flux, it will also show you. Yeah, it's a brutal. A lot of heat comes out there. So that's why I don't like to break the isolation with anything. For example, an iron stick. Don't do that. If you can eliminate these heat bridges, eliminate all of them. Because yeah, you can see I have 36. Yeah, but as you can see in the inner corner, it doesn't have anything. For example, after half meter, you can say, yeah, it's working there. Yeah, here you can see it is fully isolated. The flux is much smaller, where it's only half isolated. So that's all, folks. Thanks for your time. If you have question or something, write on the chat or send me a message. Goodbye.